Welcome to Zero Knowledge, a podcast where we talk about the latest in zero knowledge research and the decentralized web. The show is hosted by me, Anna.
And me, Frederick.
In this week's episode, myself and guest host Tarun Chitra chat with Akis Kattis, a PhD student at NYU and the co-author of a paper called Proof of Necessary Work. Now, before we start in, I want to just let you know that the ZK Summit videos are now live on our YouTube channel. If you weren't able to make the event this spring, be sure to check out the talks. Now, here are a couple topics that we covered: Plumo, Plonk, ZKVM, Circom, Fractal, Zinc, as well as new elliptic curves, new libraries, new consensus protocols. I've added the link in the show notes. Be sure to head over there and subscribe so that you can be notified as we release new videos. All episodes are actually released there as videos, as well as the ZK Summit videos and the ZK Study Club. With the ZK Study Club, we tend to do deeper, more technical talks with a group of experts. So if that's interesting to you, you might want to check that out as well. Cool. So now here's our episode on proof of necessary work. So quick change for this week's episode. With Polkadot about to launch, Frederick's availability has made scheduling a little bit more of a challenge. And we agreed that we would actually recruit some co-hosts to help out for the next month or two. And so I'm really excited to invite Tarun Chitra, who's the co-founder of Gauntlet Networks and a frequent ZKPodcast guest, to co-host. So welcome to the show, Tarun.
Hey. Thanks for having me. This was the first podcast I've ever been on. It's also fitting that's the first podcast I've ever been a co-host of.
Well, today we're going to be interviewing Akis Kattis, who is a PhD in computer science at NYU and whose advisor is actually Joseph Bonneau, who's been on the show before talking about VDFs. So welcome to the show.
Hey guys, it's good to be here.
Sort of the topic that we want to get into for this episode is this proof of necessary work. It's a paper that I saw you present, I think, at Scaling Bitcoin and at the Stanford Blockchain Conference. I think that's going to be the majority of the episode. But to start in, we should probably find out a little bit about you. So maybe you can share some context about what led you to this work. What were you doing before? How did you get started on the topic?
Okay, yeah. So I've been working on this for a couple of years now, actually. So when I started over at NYU, I was interested in a lot of the zero knowledge proof related work. But from the beginning, I kind of wanted to tackle a problem around how these things can be usable rather than how these things can be specifically designed. And I was looking more around the kind of mining architecture and ecosystem that could support any zero knowledge proof based technology. And this all led me to thinking that one of the things that would be needed if these things were to be bootstrapped in blockchains for scalability like people were using at the time, then I would need to look at the mining architecture and then potentially the kind of properties that these SNARKs would need to possess to be used as proof of work. And that sort of became and informed my context on the space. And, as this thing has been developing over the last year and a half, I feel like there's still a need to resolve this issue. So exactly how do you incentivize different entities to generate these SNARKs? And that's sort of led to this work.
Did you explore any other sort of combo proof of work, ZKP? Did you explore Zcash? Were you excited by anything else before?
Yeah, so of course. I mean, the first work in the ZKP stuff was Zcash. I still remember when they first launched and, all the different trade-offs that came out because of that. And I was looking into those things. I was very excited by the work that the Coda team was doing at the time. They're a very exciting project. And I felt like in all of those teams, it just made it more and more obvious and to me inevitable that ZKPs would actually end up being used in some form of another, and identifying exactly sort of what the issues are with creating these things and sort of designing systems and embedding that around them. It reinforced my interest in that, seeing these projects. for sure.
So one question I might ask is, I know you had worked with Coda early on in their genesis. How did working on a proof of stake version of a consensus meeting ZKP type of system influence how you thought about proof of necessary work? Because you'd kind of seen the other end of the spectrum with proof of stake.
Yeah, so that's a good question. So, for me, I've seen these two as there's basically two orthogonal directions in bootstrapping these ZKPs on payment systems as I saw it. So when I was at Coda, the guys were doing really, really good work in, getting an efficient prover, getting the setup in a way that can be commercially viable. And, there were a lot of areas that needed to be tackled and discussed around that. But as it has to do with consensus, the good thing here is that these ZKPs can be used with consensus as a black box, right? So, in proof of stake, you can encode the kind of consensus that you want, and that can inform sort of who gets to pick and choose the next blocks. And, in proof of stake, it's a different set of design questions because all of this gets encoded in the SNARK. So it has to do with exactly what kind of properties they want to get out of their system. I felt it was a very interesting thing because it crystallized in my head the fact that it can be very modular to change the consensus algorithm. But in the case of proof of work, there also have to be certain extra properties that this proof system needs to satisfy because in addition to just encoding consensus, it also needs to satisfy properties as to, what it hashes to and all of that stuff. So it did inform a lot my view on how ZKPs can and should be used, but in a way that was different to what ended up really mattering in how to build the proof of work system. It's a distinctive enough system in the design properties that it requires.
One of the topics that I really want to touch on almost before we jump into your work is the idea of proof of useful work and how I have been told repeatedly that is a bad idea. and I've mentioned, I've sort of repeated that statement, but I haven't always exactly understood why is it a bad idea. So why don't we first say proof of useful work, traditionally has been considered, not so good. I know that the proof of necessary work that you've come up with actually is, as I understand, one of the first examples where it potentially works. But why generally does proof of useful work not work?
There's many different flavors of proofs of useful work that I've seen in the literature. Some of the most intuitive types revolve around taking a problem that is useful outside of any cryptocurrency setting or any network protocol setting, encoding some kind of prime numbers that are useful or just independent problem inside the constraints and then showing that this can actually be incentivized to be created. Now, I don't see that as an inherently bad thing specifically. I would love to hear what the critics of proof of useful work have to generally say. But I do see the point that if you're providing computational power for a puzzle that isn't related to the protocol, I can see how that could be viewed as a completely outside of the system kind of benefit that most people or some users may not be particularly happy about or interested in.
I think it did have something to do with the incentives or rewards being muddled in a way, because if you say you're performing some useful work and you can sell that useful work, then there's this other economic motivation. That's what I've always understood as one of the reasons why maybe it's not inherently bad, but why it definitely complicates things or potentially could undermine some other behavior that you really want these miners to participate in.
That's actually a very good point. Yeah, so definitely. I mean, if you're performing useful work and, the output of this work has some monetary value within or without the system, then you definitely need to reason a lot about exactly what incentives you're providing each of the participants, especially in the cases where the useful work is done by the miners that are also validating and have some extra sort of enforcement requirements on top of it. Yeah, and that's why I feel there could be many different ways that this could be created, but that's why I feel that the most simple blueprint, that of Nakamoto consensus, in which the people who do the SNARK computation get remunerated the way that anybody would be remunerated when they get a block, sort of, at least in our setting, keeps this incentive one-dimensional, the same way that they would in Bitcoin. And trying and to ensure that that is the case is actually the big design challenge for us, because you don't want to be able to do things like break up your SNARK in different parts or play with the algorithm in a way that you can violate some of the randomness properties. But yeah, no, I agree that the incentive issue is probably the most important issue, and I think why this is difficult to do in the context of providing information on computation that is endogenously important.
Yeah, so I think the first time I had really ever concretely felt like someone gave a good explanation for why proof of useful work wouldn't work was like in 2014. I'd been reading one of the early drafts of Joe Bonneau's book on Bitcoin and cryptocurrencies. It's like the Princeton Bitcoin book now, but they actually tried to formalize a puzzle hardness property, which basically says if I sort of solve the puzzle that wins blocks 1, 2, and 3, I shouldn't have any advantage up to some small error of winning block 4 than anyone else. Like, and right now, I think people kind of take that a little bit for granted because they assume that there are these randomness properties. Like in a lot of the cryptography papers, you kind of don't see this puzzle hardness described explicitly because it sort of comes from the randomness that you assume exists, like whether it's a verifiable random function or something along those lines. But I think, if you go back in history, I remember in 2012 and 13, there were a ton of coins. And remember, this was the time kind of AI was sort of blowing up. There were a ton of coins that were like, solve this machine learning model and you'll get like a block reward, or do protein folding. I was working in protein folding then. So people were like, we can monetize protein folding. And of course, none of those worked because if you solved, I solved a linear regression and then I add one data point, having solved it on n data points makes it pretty easy to solve on n plus 1 versus for someone else solving it on n plus 1. So I guess I think the thing that was most striking to me about proof of necessary work is like it's the first time that I've seen something where you kind of preserve this puzzle hardness property while also doing something that's useful to the chain endogenously. And I think it's very hard to construct non-cryptographic things that have that property. I think Primecoin is also a weird example because there are certain properties of primes that are random, and then there's certain properties that are completely deterministic. And if you choose the wrong property, it might be that for like the first 1,000 blocks, it's actually random, but then at block 1,001, it's like deterministic. So maybe, I think it might be interesting to talk about like how when you were working on this, what the genesis process of getting to necessary work being in this endogenous SNARK computation was, and kind of avoiding these pitfalls. Like how did you kind of think through that?
Well, so I suspected from the very beginning that I wanted to be able to hash the SNARK the same way that you hash, the root of the tree plus the nonce, or commitment to state plus the nonce, and get something that is exactly in a black box way the same as what you would get from double shot. And from there on, we looked at all the different possible attacks that would prevent that from being the case. So we sort of worked backwards on that one. And I mean, the most fundamental issue, why don't you just take a random SNARK and hash it and do everything, goes back to, something that you mentioned earlier around if I have n data points versus n plus 1, it's the same idea. If I've generated the SNARK once, I shouldn't be able to split it up and only resolve certain parts of the SNARK that are dependent on the nonce. And this really just brings us to the notion of non-amortizability of these kinds of functions. And that's really the big challenge. And I mean, the way that we tried to resolve it involved really trying to stay within all the constraints and restrictions of needing this thing to verify state. So we wanted to do this specifically for a SNARK that verifies state transitions. And that's why we wanted to play around with the kind of accumulator that was used and modify that to to get non-amortizability. But it all begins with non-amortizability in this context, because that gives you everything else that you want.
So I think it's about time in the interview that we probably define proof. Well, like what exactly is proof of necessary work, and how you would summarize that, I guess, for our listeners.
Yeah. So the idea of proof of necessary work, it's most easy to understand in the context of a SNARK-based blockchain. But the idea is that you've got a set of miners and you've got a set of end users and a set of validators, which are the clients. And the idea is that the miners, the proof of work problem that they are providing, so the proof of work problem they're solving for security in Nakamoto consensus, is also something that you can use to very quickly extract knowledge claims about the specific state transition. So when I am providing you with a proof that this block needs to go on the blockchain, this proof is a SNARK that, in addition to demonstrating proof of work, in addition to, satisfying the difficulty condition in the standard way, also provides you with the ability to extract knowledge that indeed certain transactions do exist for this straight transition to be valid. And the process by which you generate the specific proof is this exact same way all the time. So randomly you generate this, and you ideally want it to be done so with a Poisson process or some memoryless process.
So this is this part that you're talking about where it's like, it doesn't matter if you've done one proof before.
Yeah, exactly.
You have to do the entire thing again, and it's going to be the same process, time, size, I guess.
Yeah, and that's the cornerstone of the proof of work security. So you want to be able to ensure that, so this goes back to the censorship resistant property. So you want to make sure that, if you begin working now, under some invariance over your hardware, the chances that you're going to be able to get the next block are always proportional to your hash rate. And in order to do that, you need to ensure that people can't reuse previous information that they received from other sort of tries in order to get the final answer, because then this is going to mess up with the incentives, as you mentioned, and that's really no good, because then we don't get the security that Nakamoto is based on, and on which we can then make claims about consensus.
Cool. You mentioned, just in your explanation, you mentioned validator, but I want to distinguish that, because I believe it's not validator in the proof of stake context. It's validator. No. What is that? Is that like a like client validating? Is that what you're thinking?
I just meant something like in terms of the verifier in all these proof systems, like prover verifier. So the verifier here, we're just assuming, has very little memory. It's just a smartphone. It's like sort of like a light client or an end user that would basically just be checking a SNARK proof. Another thing I think people often hear, but is sort of important to light clients, is incrementally verifiable computation and recursion. And so maybe, do you think you could walk us through how that plays a role in this construction and why it's important? For sure. So actually what I would like to first say is that it's not really necessary for this construction. It's not something that, if you don't have incrementally verifiable computation, you won't be able to use this construction, but rather that it works with this construction. So if you do have some sort of blockchain architecture that is doing a PCD or IVC, then, as long as the way that you generate the specific predicate is done in a way to ensure that no or very little information is reused, then you can do that absolutely no problem. So you don't actually need any cycles or any recursion to do this. In our prototype, we did do that. We just wanted to make something that, also has recursive verification. And the main really cool thing that you get out of all of this is that you can basically take light clients that can verify the whole chain, but in addition to verifying the whole chains, they can also verify that proof of work has been computed at every single step. And they can do that with the same guarantees that they would do in IVC. But that's not strictly necessary. You can have a context in which miners can do almost everything outside of the SNARK, except for some very basic operations inside that, correspond to the accumulator of the specific blockchain. And then, light clients would still need to verify every single state transition if we don't do recursion, or if you just specifically work with block SNARKs.
I'm still not entirely clear on what incrementally verifiable computation is, though. So like, I did understand it as similar to recursion, but you're saying it's not.
Oh, so IVC in general, I just mean that formal computation that builds on previous steps. So this is how we model the state transitions in the blockchain. And the design question then here is, do you want to verify the SNARK of the previous block in the next block? So do you want to actually specify the verifier out and actually do all of that specific computation? Or do you want to be doing that outside of the SNARK and be doing it in the normal way? That's the distinction that I meant. And proof of necessary work is really invariant to this design choice. That really depends on how much work you want your light clients to be doing versus your miners, which is orthogonal in a sense.
One of the points in the paper, like you do talk about light clients at one point, and you cover a few different kind of accumulators or ways that light clients are generated. You mentioned fly client, and then you mentioned NIPOPOW, which I had never heard of. What is NIPPO? I don't know if I'm saying that right at all. But
so I think it stands for non-interactive proofs or proof of work. So it's an idea that goes in the same vein of resolving similar issues. So the question is, if I'm at a block height or if I'm at a certain level in the system, and I want to receive, or I want to have prove knowledge to myself that, this specific chain height actually has done all the proof of work. It's just a different way to do this that asymptotically does better than standard Bitcoin. I think that they do it in logarithmic number of blocks based on the way that they check for proof of work. But it's really just another way that ensures, when I get the block height, instead of really needing to go back and double check all of the hashes work out, that I can do that more efficiently. In a sense, it's a very similar kind of question to, I want to verify all state transitions if part of the state transition is verification of proof of work. So in a sense, you can consider them as similar, but it's just a more specific subset for the proof of work verification itself. And the reason that we built the design using recursion and using all the PCD stuff was because we wanted to demonstrate that this kind of approach is also capable of doing that verification in constant time, the same way that it would do the state transition verification in constant time. Even though in practice, if somebody wants to build it without recursion, that is still feasible. The puzzle is still going to work out.
Yeah, one interesting thing I think that Anna's point kind of points out is that non-interactive proofs of works are quite old. I think it's like an Andrew Miller paper from 2014. But there's a sense in which people's memory is always tied to whatever papers they read first, where they saw definition of X is blah, blah, blah. And they don't understand sort of sometimes the history of why that definition is good or useful or has shown up. So it's kind of interesting to think about how cross-chain communication research, if someone started in 2016 versus starting in 18, they would have a very different vocabulary because they'd be referencing a completely different Genesis paper that they'd be looking at. Are there any things that while you were working on this you kind of felt like you started on the shoulders of giants to the point that you don't even know necessarily the history of? It just was oh, okay, everyone assumes that, so it must be true.
Well, that's a great question. I mean, there's many different parts to sort of what is needed to get this to a great design, that a lot of that work, had to happen before this question is even relevant. So, when in 2013, 2014, you've got, Merkle trees that use SHA with millions of constraints, So the one dimension is how fast these SNARK proofs can be generated. And that's also something that introduces some trade-offs in our model that we should probably talk a little bit about. But yeah, one thing is, the community that's been working on designing faster SNARKs, that's bringing down proof generation time. That's also bringing down proof sizes because we want to be putting all this stuff in the blockchain. All of that work, absolutely, that needed to be done before what we did is even relevant. In terms of taking assumptions that other people, have considered to be standard, the Bitcoin white paper is written in the random oracle model. They've got a very specific setup. And I just felt like, we just really wanted to deviate as little as possible from the Nakamoto proof, so the Bitcoin paper argument as to what the specific, hash functions should do. And that's why we really didn't want to change very much from, the hash cache, the proof of work based constructions, but instead just literally switch out one very specific part. So just switch out the SHA. But we wanted to make sure everything else remained the same as much as possible.
It's a proof of work system. Mm-hmm. How does the mining, how would a miner act? What does their actual work look like? Because they're also, as I understand it, they're also generating a proof. Mm-hmm. And are they doing anything else? Maybe just say, what is the action of this miner?
Yeah, that's all they're doing. And they're doing it over multiple times. It's already a lot of work, so it's not that we can make them do much more. They really don't need more. They really don't need more. Yeah, so they can make the SNARKs bigger. So the main idea here is that, you've got a mempool. Mempool has transactions in it in the exact same way as Bitcoin. And in that mempool, you just pick a bunch of transactions out, you stick them in a SNARK, you generate the SNARK with a very specific nonce that's also randomly generated. Think of this as, you generate your block and then you're hashing your block along with a nonce. It's exactly the same idea, only that instead of putting them in a block, you're putting them in a SNARK. And then you generate your SNARK, so you do all of the different parts of the computation that are needed. But notice that because the nonce is also part of state here, so it's also part of your inputs, it's going to affect what that SNARK looks like. It's going to affect your proof of knowledge claim. The aim in this is that it affects it in a sense, it affects as many variables as possible, so that then, you check at the end, so you get a proof out of your prover, you hash the proof, and then you check if it satisfies difficulty. And if it doesn't satisfy difficulty, then you change your nonce randomly. You can keep, the state transition you wanted exactly the same, and then you repeat the process. And the idea is that every single one iteration of this needs to reuse zero information from everything else. And then at the end, when you do find the answer, you post that on your network, so you broadcast your SNARK proof. Everybody verifies, checks that it's correct, verifies the updated quality, and adds it to their sort of head block.
But do the other clients also have to run the SNARK somehow? If you're saying that they're do they have to do all of that work as well?
No. So the proving side work is something that you also need to have state for. So you need to be able to actually have the specific state transitions for. So in this model, all of the miners have access to this. That's a lot of stuff. There's a big proving key in there. And they have access to all this in order to generate the proof. But the important thing here is that indeed the entities that are double checking that we're at the right quality, we're at the right level, don't have to be the miners themselves. Those can be light clients. So the light client just has a verification key, checks that the SNARK is correct and that it actually corresponds to, the deepest block, and then, hashes it themselves to check the difficulty and the proof of work was performed, that this is actually legit. And that's all the verifier needs to do. Now, if they want to keep a copy of state, they also need to process all these transactions, and that's sort of the data availability side of it. But that's really the main setup.
And in terms of data availability in this model, there is sort of a difference than Bitcoin in the sense that the light clients are meant to be thinly data, they don't actually store all the data, and they kind of act as these endpoints. How does that play into sort of the economics of this, and how mining pool dynamics will grow if the mining pools end up needing to be the pools that have the most state stored, or there's kind of the state burden that's kept on mining and proof generation? How do you imagine that affects kind of how concentrated or how dispersed mining pools will be?
Yeah, so I feel like on that issue, we looked at the question of light client verification in the sort of classical sense that people have been looking at. Assume you don't have the ability to store the whole blockchain, what can we do for you from a verification perspective? But we need to ensure that, everybody who's mining, everybody who's updating the Merkle tree or the accumulator needs to have access to the state. That's really the main hard constraint here. But in a sense, that's the hard constraint for anybody that wants to do a state transition anyway, just because they need to know exactly what the updates are going to look like. The main bottleneck that comes out of this, if you want to retain the trust model that you have in cryptocurrencies like Bitcoin, is that in a sense, you've got to put all of this data on chain so that everybody's going to be able to recreate the state transition. Now, I don't really feel like the really big burden here in terms of mining pool centralization rests on whether the miners have to keep state or not. That may be the case if the chain is, multiple terabytes long. But I feel like the main question there is just how non-amortizable can you get prototypes that, solves these specific functions. I feel like that's more of a factor on how big the mining pools are going to get. Because of course, you can also sort of checkpoint in the blockchain and sort of keep a lot of stuff in the back. Of course, there's corresponding trade-offs in the model. Yeah, but I don't really anticipate that the biggest bottleneck to centralization in these systems is keeping the state, but rather how well can you optimize the specific function, which in our case is a SNARK proof generation. So how low can this go in comparative to other people in the system?
But is there actually a difference between a big miner's ability to do this versus a small miner?
Yeah, so that's really goes to the core of this. I would say there's one dimension in which we can distinguish between big versus small miners, and that's specific to solving SNARKs that are based on elliptic curve operations. So there's so this is all the Groth 16, Pinocchio, all of that sort of flavor of SNARKs, not stuff that's based on Fry or Stark-based stuff. But, in that context, which is, what we built this around, there's, one main, so there's basically two main operations that matter. There's the fast Fourier transform that's done in order to generate polynomial coefficients. And then there's the exponentiations that are done, which are to generate the specific SNARK. We focused on the exponentiations, which is also the asymptotically sort of hard parameter. And the idea is that, exponentiation is amortizable. So that's, a fact about exponentiation. So if you want to do this kind of process while using exponentiation in these elliptic curve groups, you need to be able to understand the trade-off between pre-computing many of these values and not. And really then the question becomes, if I have a pre-computation table that has every single potential value for, this, then I can solve this problem easily all the time.
Faster,
right?
Yeah.
Yeah, and that's,
Or is it actually faster or it's just more often?
Well, if I just have a pre-computation table with all the potential values, I can just resolve it and faster all the time. I literally just query the specific index and then here we are. So, however, this is not feasible in practice because you would require exponential space. So the amount of space that you would require for this is really dependent on, how many of we can go more specifically into numbers, but it's really akin to enumerating all the exponents for all the different bases in your proving key. That is gigantic. So that's not really going to be how you can differentiate between bigger and smaller miners. What I think you'd see people doing in reality would be to use some of these pre-computation sort of optimizations up to a certain level of space and then being able to bring down their computation time. Although that, in a sense, technically wouldn't affect the system because that's something that anybody would be able to do because that's a pre-computation table that everybody can generate at the beginning. This would be a problem in the case that, if you just add a corresponding amount of extra space, you get substantial speedups. But on the asymptotics of this, the amount of space that you would need to achieve, 1% speedup at every level goes up exponentially. So there will be a certain point where there's going to be a good enough table that miners are using, based, of course, on the memory that they have. And then overall, the rate at which they churn out proofs is going to be very similar, and the changes are going to be negligible. So that's really the main way that I would envisage a difference between a big miner and a small miner. Specifically to the case when you do elliptic curve cryptography, in order to generate your SNARKs, this trade-off is better understood by us. So you do end up with exponential space on that front. Now, when it comes to other kinds of SNARKs that don't use, Kate commitments, that's a very different sort of area. I don't have any specific and, succinct results on that one yet, but I think that it would be much easier to do this without that kind of trade-off. So that would strengthen the non-amortizability properties of the system, but that remains to be seen.
Sorry, when you say the non-Kate commitment, you're referring to structured reference string type of systems. Okay.
Yeah. I should have made that clear. Yeah. So we all of this comes from the need to compute Kate commitments using the universal structured reference strings that or non-universal that they have in Groth and in some of these systems. Haven't looked at other systems though that don't do that. That would be interesting.
This is a side note, but is it Kate or is it Kate? Because I've very much heard it pronounced the other way.
Oh, really?
Does it have an accent?
I mean
the Kate?
No, so
right.
it's an Indian. So it's Kate, but
okay.
But
well.
like all Indian people, you just kind of don't really care about how people pronounce it in the US.
I had no idea. I see. So it's not Kate. I need to relearn that. Okay, it's good to know.
The rule of thumb for Indian names is add an H before or after every vowel.
Oh,
so what's your
like
name?
An implied H.
How do we pronounce your name correctly?
Don't pronounce it correctly because no one else does it. It would be weird. But it's like, if you were saying it like my mom says it, it's Tarun.
Tarun. Oh wow, cool.
So Kate is Kate, but
Kate. Okay, Kate commitments. All right, I will definitely.
But I think everyone says Kate, so they'll probably not know what you're talking about.
Except for Ariel Gabizon, who says Kate and has said it on the podcast. So I just wanted to be sure.
Yes. He's much closer to the correct. That's much closer to the correct.
Okay, that's good to know. All right.
I mean, maybe, yeah. Sorry, side note. You should include that in this.
I will, for sure. That's awesome. I have no idea how to ask this question. I have written define adaptive throughput because I don't know what it is. So
maybe one way of saying it is, one of the big advantages to this method is that you can have block sizes that vary, which means that the throughput of the blockchain doesn't have to be constantly 500,000 transactions per second, but have empty blocks. And it also doesn't have to be slow, like 6 transactions a second. You can have, when there's bursty demand, it can go up to a lot of transactions. And when there's not many, it goes down, which means that the economics can fluctuate with the true demand rather than kind of being a little bit having a floor on the economics. And so, that adaptive throughput has kind of been this holy grail that I think in 2017 people forgot because everyone was just selling TPS as a
feature,
a key metric, feature metric. I don't know what to call those days because I think a lot of the people who sold that also maybe were just trying to fundraise and stuff.
Using fun buzzwords, I guess.
Yeah.
The 2017 years.
Exactly, but there's kind of this benefit, cryptocurrencies are in some sense the ultimate Veblen good. So Veblen goods are these goods whose price increases when demand increases, like Supreme, the clothing thing where people are waiting out. That's a Veblen good. So adaptive throughput is somehow this holy grail of turning this cryptocurrencies or Veblen goods into something that makes the demand model make sense. So how does that show up in proof of necessary work? How is it used? How does it, kind of walk us through maybe? the economics of that?
So this goes really back to the issue of incentives that we discussed at the beginning. So in general, when you are computing a proof and you've been able to bootstrap in there that you've also verified certain transactions, that really is a necessary but not sufficient condition in order to get adaptive throughput. And so really what we mean by that is that ideally you want a system whereby the amount of demand and the amount of supply for transactions, so this is sort of the setup here, is something that is always clearing. So it's something that, if you see transaction fees go up, you would rather want the system to sort of take note of this fact and then grow its TPS that it provides, accordingly. And the way that, the end user would see that is that this would put downward pressure on the transaction fees, mainly because you're producing more of the good, where the good is, rate of transaction processing over time. So you would like a system that endogenously adapts for this fact. And, if you use something like proof of necessary works, where you're in a sense saying that, I've got a SNARK, this SNARK has S transactions in it, and I've generated a proof of this fact, and I've put it on the blockchain. We noticed that at this point, we've been able to make difficulty, what people in the economics discipline would call a sufficient statistic for demand. Because, if more people would like to use this, then the transaction fees are going to go up. It's going to be more profitable to mine. More miners are going to come up. Difficulty is going to go up. And the problem with doing something like this as is on Bitcoin is that in a sense you're constrained to one dimension. If you would like to keep difficulty very low, that imposes security questions on the protocol. So if you've got very low difficulty, somebody's going to attack it, and that's something that means that difficulty in a sense is something that's a peg both to feasible demand and both to security. So you really can't decouple those things. Now, in our case, the cost, so the security, is actually a function of two things. It's a function of the difficulty, but it's also a function of the size of the predicate, namely the number of transactions. So, if you've got more transactions, it's going to be more difficult. And, if at every single step, at every single block, the only kind of predicate that the system takes in is one that has, let's say, S transactions, then that's something that you can vary over time, is the main idea. So, difficulty goes up. And then you can have a second update rule. So, you've got your standard difficulty update rule. And then, difficulty goes up when there's more demand. But then you have a different update rule that updates at a different, separation of timescales. And that actually acts to change the size of the SNARK block in a way that also affects difficulty. So, in the case that difficulty goes up by 1, twice as many people are mining, that corresponds to the fact that you've got higher transaction fees, which is why more people are mining, and then the system is going to actually increase the size of the predicate, double the size of the predicate, to be able to drop the difficulty back by 1. And so in a sense, it's sort of like a system with gears. So, you've got, difficulties going up until there's a change in the predicate, and the predicate size goes up or down, up in this case, and then difficulty immediately drops down again. And if you keep difficulty at a constant level, you're actually capable of having a constant level of transaction fees as well, because all of the security guarantee that the proof of work does actually goes into the fact that your SNARK is much bigger. So you don't actually have to compromise on security because you decouple the efficient statistics for both security and demand in this context. So this is why I think that something like this could be used for adaptive throughput guarantees, with the ultimate aim being keeping transaction fees constant regardless of the amount of demand that comes into the system.
So have you really cracked this, or is this still like a work in progress?
So this specific thing, we haven't built this specific part using bits and bytes, but we do have a paper out that outlines this idea, and we do have formal guarantees around this in the Bitcoin model. There's specific kinds of relationships that the hash rate, so the proof production, needs to satisfy in order for something like this to be incentive compatible. Our formal result is a general equilibrium result on this. So if we look at demand shocks of systems that run this kind of double adaptability rule, so the difficulty part and the predicate size part, And we're able to show for specific update rules that you can stabilize so there exists a stable state equilibrium for the transaction fees regardless of the size of the demand shock, well, with a specific upper bound. And we're able to show that for a system that models the supply side and demand side of Bitcoin. But that's more of a theoretical contribution. But the idea is still there that this is basically free with a little asterisk to build on top of systems that run proof of necessary work or succinct blockchains. That's this kind of adaptability you can do outside of the SNARK. So there's no real big design issues. It's just a question of ensuring that the system is going to be able to price in any demand shocks and then always sort of like over time converge to a point where you're still at the same initial level of transaction fees. Basically, I like to think, and Tarun did mention this a little bit earlier, like I like to think of a system, like a decentralized system as one that doesn't immediately begin with 10,000 TPS, or at least the ones that have existed. If we're looking at decentralized systems, it's really just a function of how many people use it, right? And in decentralized system, this kind of thing is going to grow organically, usually, and we feel like, we felt in that paper that TPS also grows organically in this sense if you do have this sort of incentive link between the generation of the proof of work, which you're forced to do, and the generation of a proof of work that also verifies transactions whose size you can calibrate. And it's really the latter part that allows you to then adaptively change how big each specific predicate update is, so you can actually take pressure off of the fact that, you've got a constant block size. And you take pressure off that by growing, in a sense, the system. And so, if transaction fees are really high, predicate size is going to get bigger, difficulty is going to go down. So that's really the main idea.
So, I think one of the most interesting things about this, right, is that, in Bitcoin, I'd say the biggest seminal event in Bitcoin post-Genesis was the block size debate. Mm-hmm. And the block size debate obviously is kind of thrown out by this world where you have constant size blocks powered by SNARKs. And that's the reason you can get these kind of constant transaction fee under bounded, demand shocks limits, because the block size physically in bits is not changing, but the block size in content information wise is actually fluctuating. Mm-hmm. And separating those two is what gives you this economic abstraction. This is a very proof of work thing because it relies on difficulty adjustment. Do you think, and especially since this is, I remember when Joe first brought this up at the kind of reading group at NYU, which is where I actually first met Aki, was like, oh, this is proof of work coda. So the interesting thing is the difficulty adjustment is fundamentally different, and I don't know how you can, if you can, replicate it in proof of stake. And so that big difference between coda and proof of necessary work, what is there a way to actually do a staking version of this, or is this fundamentally a difference that can never be replicated in stake, like this kind of demand adjustment?
So that's a great question. I'm not so sure, actually. That's a very good question. The only thing, we had a modular approach to the way that we tried to prove these things. Now, if there is a proof of stake kind of consensus mechanism where you have a certain parameter that functions in a similar way as difficulty, so in a sense that it's the proxy for transaction fees, then, for demand, then this can absolutely work out. That can just be plugged in there. I'm just struggling. So I don't actually know very, very much about, the most cutting edge or the latest in the proof of stake literature. But, if that kind of property can be isolated and you can figure out a way to make sure that it isn't affected by the size of the predicate in the same way that we have here, then that should be able to be plugged in very modularly. I just haven't actually looked at how this can be done in proof of stake. Yeah, and there may be some issues if you don't actually have a parameter like difficulty there.
On a kind of another note, how would you add, is it possible to add smart contracty stuff into this model? Does it work?
Yeah, I mean, this is a SNARK, right? We built our prototype based on transactions that move pebbles, but you can do anything, right? Like it's in NP, you can, the kind of transactions that you can be verifying could be other SNARKs that could be arbitrary computation, for example. That technically is possible. And there's different trade-offs there because all of that is very expensive. We didn't discuss any Asics or FPGA sort of stuff, but that may be feasible then. But yeah, I mean it's really invariant. You can make your state transition whatever you want.
Yeah, so everything that kind of has been surrounding proof of necessary work actually sounds super appealing, especially given that there's been such a huge amount of resources committed to trying to make proof of stake versions of these types of things working, but kind of less on the proof of work side. So I'm kind of curious how you see the direction of implementation going, and how you expect kind of the first version of proof of necessary work in production to look. Will there have to be GPU miners only? Will there be FPGA miners, ASICs? Like what, kind of how do you foresee the next 1 to 5 years?
So I think that's important here to highlight. You bring up GPUs, FPGAs, etc. So the number one thing I would like to highlight here is sort of what our trade-offs are. And this kind of system only works well if it's very quick to iterate over many different SNARKs, so many different proofs. Otherwise, it loses the asymptotic properties that you want, and this is all in comparison to block time. So that's really the ratio that we care about. And that, it leads to some security implications if this ratio is too high. So I think any implementation is going to need to take this ratio down. So the ratio of time to generate one proof to block time. As long as that's something that you can do in deployment, then the system is going to be secure, at least on this front. Now, whether you're going to need FPGAs or GPUs or what kind of specialized hardware for this, that would be great. Specialized hardware is going to make everything much, much faster. It's going to give us these 10 or 100x, increases in efficiency in a lot of these dimensions, including TPS and in other contexts. Now, I'm not so sure exactly the kind of model that this would be implemented in initially. It's it can work, as I said, both in the recursive and non-recursive context. If I were to sort of speculate, I would say that in the first sort of ways that if this was going to be deployed, then you wouldn't really have a full-on, fully recursive system that, is, can do adaptivity to really, really large really large predicates, and then also satisfy the fact that each SNARK is generated in like less than 1 second, and also have 30 or 45 second block times, right? That's sort of where we want to get. That's the kind of system that we want to see. But, getting there can happen very incrementally. You can build a system, for example, the kind of work Coda's doing, where recursion is a very big part, and you can put it in there. You can build a system where, you make those SNARK generations more efficient, only you sacrifice, certain other properties. You could even do this in a trustless SNARK, although that's going to be less efficient. So it really depends on the kind of design goals that, anybody that wants to implement this has from the beginning. But the ultimate sort of endpoint for this is that, you want to be able to generate really, really large predicates. And you really want to bring down this bottleneck that, if I actually have a big enough system where I need to do 100 transactions per second, I better be able to generate a really, really large SNARK. And for me to be able to do that, that's probably going to, at least, unless somebody comes up with the ultimate SNARK, which they might, you never know, that's going to require hardware acceleration, and it's going to require ways to be able to resolve the fact that these things also take a lot of memory. That is both a feature and a bug, depending on how you build that. So yeah, that's, we'll see what happens if people want to use this, and if this is something that, they're going to use on a more simple payment system or a more general one. It depends on a lot of these factors, I would say.
A few weeks ago, Tarun and I actually did a talk where we were kind of talking about like this idea of monetizing privacy, and this proof of necessary work was like a component in that idea. It's actually an idea that originally came from a talk that Tarun did with Georgios at the ZK Summit. I wonder, I wanted to sort of wrap up this interview with just like a little chat about this, because I don't think we've talked about it on the podcast before, and it might be interesting for people to start thinking about it.
Yeah, so I think one interesting thing about the philosophy difference from going from sort of traditional proof of work to SNARK-based work is that, traditional proof of work was monetized by just evaluating a hash function and having sort of this VDF-like property, but like instead of it being a delay, the delay is given by the hardness of the hash function, or like the discrepancy, I guess, something like that. But I think especially if SNARK proving becomes a form of monetization because it serves as the security bond for the network, in some sense, you can tie the security bond of the network to some type of privacy preserving aspects of a blockchain, because you've now found a way for people who are generating proofs that can be potentially that are preserving to some extent privacy if the SNARK is, say, verifying the state transition of a bunch of transactions on a blockchain, but not putting all the transactions on chain. You're basically rewarding people for preserving privacy versus, normally you reward people for violating privacy. So, how do you see, say, proof of necessary work as something where society can actually provide a mechanism for rewarding people for preserving privacy instead of sort of the monetizing one's data?
So, first thing I'll say is I think the dream is good. Figuring out an incentive compatible way to ensure that the privacy related stuff is resolved. I think that's the kind of right approach. Now, in terms of how I see this fitting into the kind of work that we've been doing, in a sense, I think of it as something that allows for a skeleton sort of chain in which people can plug in SNARKs of arbitrary computation. In the sense, I would take a step back and say, it's really just an incentive compatible sort of backbone in which you can plug in verifications of specific kinds of computation. And the privacy isn't so much on the transaction between two entities, but rather on the privacy of the computation that is being done or that is being verified. So I just see that, proof of necessary work as a first step towards trying to realize a system whereby you are able to find a counterparty that's going to mint verification of arbitrary computation for you on a distributed ledger that's append only. And I feel like that sort of goes into what you're saying, in the sense that the privacy of the computation is something that's a feature in all of this. And it's something that people are incentivized to do because the rules basically spell out that this is what you've got to do. And but I see proof of necessary work in the context of, enabling the maintenance or in a decentralized way of an append-only ledger of records. So in a sense, it's record keeping, only that it's in its most general form that, if you use the right SNARKs or any of the SNARKs people use, you can get these guarantees in zero knowledge. And that, I feel, sort of comes on top of it and allows you to basically keep that kind of ledger out there, because that's really the hard part, right? Being able to maintain this thing without having centralized parties.
I would love to continue that conversation, that idea of like, by monetizing privacy, potentially making it more than a nice to have, but like deeply embedded in sort of a feature set. It comes along with the incentives. It comes along with like the entire building block of the protocol. But I think for this episode, we kind of have to wrap up, which is a shame. But it's been such a pleasure, and it's been really fun to explore this topic in way more detail. I definitely am walking away understanding it a lot better. So thank you so much.
Thanks a lot, guys, for having me. This was fun.
Well, I'm just a guest, so you should.
Well,
really
you're the guest. You're the guest host. Tarun, you're the ghost.
A guest host.
Tarun, I want to say thank you so much for coming on as the guest host this week. I really liked having you here. It was cool.
Thanks. Hey, it was fun.
All right. So then I guess to our listeners, thanks for listening.